So, in the last class we talked about electric fields which are generated inside this p-n junction because of diffusion of these majority carriers from one side to the other side and vice versa. So, that board is still here. So, we can talk in this reference. We have this p-n junction, this side is p side and this side is n side. So, when you have these acceptor impurities, you create lots of holes and those trivalent ions are sitting at the lattice sides. And when these holes move out, then those ions will have negative charge. Total charge was neutral, but then once this hole has moved there, those ions which are there, that those trivalent material that we have doped, they will give this negative charges. Similarly, on this side you have donor ions. So, the ions come with 5 conduction, 5 electrons in the outer orbit, and so those electrons are there, free charge carriers are there. But then when these electrons, these conduction electrons, when they move out, those ions, positive ions will be there and you will have this positive charge here. And then we take this approximation or this limit in which we say that the charges are constant in this region up to a width x1 here and a width x2 here. So, this is that rho versus x distribution, and then from here we calculated E versus x, and that was this. Now, today we will be talking of a potential difference across this junction. So, to calculate that, we have this electric field. Let us try to do in this region right to the junction. So, we have this expression here. The electric field, total electric field is given by this expression here. This is the one. So, this total electric field is minus rho 2 over epsilon and then x2 minus x. It is this straight line. This is straight line here. Okay, so now let me erase the other parts. So, you know the basic definition of a potential difference. This is dV is equal to minus E dx for one dimensional case, and so here it will be rho 2 over epsilon and then x2 minus x and dx. So, if I integrate, you get V is equal to rho 2 over epsilon then x2 minus x square by 2 with a minus sign because you have negative sign here and plus some constant. And that constant can be evaluated by just choosing a point for V equal to 0. So, we take this junction point itself, x equal to 0 itself, as the point where V is 0. That is our choice, you know that. So, take V equal to 0 at x is equal to 0, and then you get 0 is equal to x is 0. So, it is minus rho 2, x is 0. So, x2 square and divided by 2 epsilon plus c. So, c is rho 2 x2 square by 2 epsilon. So, you can write this from here, you can put that c there and you get V is equal to minus rho 2 over 2 epsilon and then x2 minus x square and minus this x2 square. So, let us check at x equal to 0, V should be 0. So, at x equal to 0, it is x2 square minus x2 square, that is 0, that is fine. So, we have substituted it correctly. So, this is the expression for V. And what is V at x2? V at x2, at x is equal to x2, V is equal to, so x is equal to x2. So, this goes out. So, it will be rho 2 x2 square over 2 epsilon. right? You put x equal to x2, so this is 0, this is plus rho 2 x2 square by 2 epsilon. It's a quadratic function. It should be. If electric field is linear, then the potential has to be quadratic. So if you plot, how will it look like? So the expression was V equal to minus rho 2 over 2 epsilon, and then x minus x2 minus x square and minus x2 square. So at x equal to 0, this is 0, and x equal to x2, it is at x equal to x2, it is V equal to rho 2 x2 square and then divided by 2 epsilon, right? This is 0 here, and then rho 2 x2 square and by 2 epsilon. So if you plot, if you draw x this direction, v this direction, it's 0 here, and then this is say rho 2 x2 square over 2 epsilon, and at x equal to x2 it must be this much, so it's here. And then it's quadratic, and also remember the slope of this v versus x is electric field in magnitude, and here the electric field is like this. So the magnitude of electric field is largest at the origin. So v versus x should have largest slope at the origin, and then as the electric field decreases, the slope should decrease, and at x equal to x2, this slope should become 0 because the electric field is 0. So it should be of this kind. It should be of this kind. Right? So that should be the kind of plot, quadratic, joining this point, and slope gradually increasing. Slope gradually decreasing as you increase x, and beyond x2, right? Beyond x2, that means in your PN junction, this is x2 and this is minus x1. So beyond x2, here in this region, this is the depletion region. So in this region, there is no electric field, and so the potential is constant. So throughout this n-type region, this is n-type, throughout this n-type region, the potential remains constant like this. Same is the story on the p side, or x less than 0. X less than 0, if you write, is the same algebra, identical, and this v will be at x is equal to 0, we have taken v equal to 0 anyway, and at x equal to minus x1. It should be quadratic. Remember, the electric field is just of this kind, so linear, so it has to be quadratic, and at this point, you can take the similar expression from here, v is minus rho 1 x1 square by 2 epsilon. So if this point here is minus rho 1 x1 square over 2 epsilon, and this point is x is equal to minus x1, then you have to join this point and this point. So this comes like this, and then it turns, and here the slope should become 0, and then it should become constant. So that's the kind of potential variation across this junction as you go from p side to n side. So this is at a lower potential, this is at a higher potential. There is a built-in potential inside this material. No batteries, nothing, but there is a built-in potential difference here. And this difference is known as the potential barrier, This difference is the potential barrier. You give some name to it, let us say call it VB. So, how much is that VB? That VB will be this rho 2 x2 square by 2 epsilon plus this rho 1 x1 square by 2 epsilon. So, VB will be rho 2 x2 square and plus rho 1 x1 square and over 2 epsilon. That is the barrier. It is in terms of rho 1, rho 2, x1, x2. Let us try to write that width of depletion region. Width of depletion region, relation between that and this potential barrier that we have calculated. So, what we are interested in, that width of the depletion region, which is x1 plus x2. x1 plus x2. This x1 and this plus x2, this is the total width of the depletion region. You have one more relation, and that is rho 1 x1 is equal to rho 2 x2. Right? Charge neutrality, rho 1 x1 should be equal to rho 2 x2, because the charge here is minus rho 1 times x1 times that area of cross section, and the charge which is here will be similarly minus plus rho 2 x2. And since this total should be 0, after all we have not put any charge in this material, so this relation. From these we can write capital X in terms of VB rho 1 rho 2, eliminating x1 and x2. So, first step is write this rho 1 x1 as rho 2 x2. Use this equation here. So, this is equal to, this VB is equal to rho 2 x2 square plus rho 2 x2 and x1, right. This rho 1 x1 is rho 2 x2 and one more x1 here. So, it is this, and you take rho 2 x2 common and you get x2 and plus x1, which is capital X. So, this is 1. Now, you have to eliminate this x2, and that you can do from here. This x1 and x2 are in inverse ratio of rho 1 and rho 2, and the sum is capital X. So, x2 will be rho 1 divided by rho 1 plus rho 2 and times capital X, and x1 I do not need that, but x1 will be rho 2 divided by rho 1 plus rho 2 and then capital X. Okay. If you add these two, what happens? If you add these two, you will have rho 1 plus rho 2 in the numerator, which will cancel this rho 1 plus rho 2 in the denominator, and it will be x. So, x1 plus x2 is capital X, this equation. And if you multiply this x2 by rho 2 and this x1 by rho 1, they become the same. So, rho 1 x1 is rho 2 x2. So, this is it. Use this expression of x2 here. What do you get? You have rho 2, you have capital X and then 2 epsilon, and then this x2. So, put rho 1, so rho 1 here, and then capital X, so square of this, and then divided by rho 1 plus rho 2. That is this VB, potential barrier. So, if you want to write capital X from here, this capital X will be, take this thing here and this thing down and then square root of it. So, it is 2 times epsilon rho 1 plus rho 2 divided by this multiplied by this VB here and divided by this rho 1 rho 2 here. All right. X square. So this will go here, 2 epsilon rho 1 plus rho 2 into Vb, and then divided by rho 1 rho 2 and then the square root. So this is it. So you have a relation between this depletion layer width and this potential barrier, but this rho 1 and rho 2 are coming here. Okay, can write this as 2 epsilon and then Vb and then 1 by rho 1 plus 1 by rho 2. These rho 1 and rho 2 are related to the concentration of impurities that we have doped, right? Because how are you getting charges in the depletion layer? In the depletion layer you are getting charges because you have put impurities. This is P side, so you have put acceptor impurities. Acceptor ions are there, right? When you diffuse boron, for example, or any trivalent atom in silicon, then you have created a hole there and then the ion which is there, and this whole thing is neutral. So same thing is here, same thing is here. Here holes are still there, holes are still there, and therefore there is a charge neutrality. There is a charge neutrality, and here the holes have migrated to this side and recombined with electrons, or electrons have come here and recombined. This charge carrier has gone. So those ions which are there, those will still remain there. The hole has moved and recombined and has gone away. Therefore, you have this negative charge. All right. So each acceptor ion which is sitting there in the depletion layer is giving you 1 unit of negative charge. So the charge density will be just E times and this density of acceptor ion. So this rho 1 here, okay, this charge density rho 1 here in this region is just E times Na. What is Na? Number of acceptor ions per unit volume, right? Number of impurity ions which I have doped here per unit volume. So that is Na, density, number density. And then each ion has this charge of minus E, and therefore this rho 1 is just E times Na. And similar is the story on this side. Similar is the story on this side. On this side you have put donor ions. If it is silicon, you have put pentavalent impurities here, and this pentavalent impurity comes with extra electrons. So those electrons were there, here also, and this whole thing was neutral, but from here the electrons have gone, and therefore those positive charges will appear here, those donor ions, each donor ions, and will give you 1 unit of charge, E plus E charge, and therefore rho 2 will be E times Nd, density of donor ions. And this expression you can write in terms of Na and Nd, because these are the quantities which are under our control. We dope things, so we know what is Na and what is Nd. All right, so what is the final expression? So this X is equal to square root of 2 epsilon Vb, and then here I write 1 over Na and plus 1 over Nd and E here. So that's the relation. So if you increase this concentration, what will happen? If you increase Na or ND or both, what will happen? This increases, so this whole thing decreases and this decreases, right. So heavier is the doping, smaller will be the depletion layer, and vice versa. Okay, so that's it. Now this VB is something which still we do not know, right. So, and that VB in fact depends on, that also depends on the dopant concentrations and also on temperature. So, I will not give you those derivations, but I will give you the expression for this VB in terms of those impurities and the temperature. And that is, this VB is KT divided by E, then log of, on the natural base, Na Nd over small ni square. You remember we have introduced all these symbols. This is Boltzmann constant, this K into T, Boltzmann constant into temperature in Kelvin, electronic charge, Na, Nd are the densities of acceptor and donor ions, and this Ni is the Ni is just Ne and Nh, which are equal for intrinsic semiconductor before doping. So that is this Ni. So this gives you this expression for Vb. All right. So the next thing I will take up is the energy band diagram of this semiconductor, this p-n junction, and the effect of this potential difference that is created, internal potential difference that is created on the energy band diagram. So if there is no potential difference, you only have a p type semiconductor and n type semiconductor in the same original material, then the conduction band is here, the valence band is here, all these energies are valence band energies, all these energies are conduction band energies. So you have this bottom edge of conduction band here and the top edge of the valence band here. So same is the case with p type, same is the case with n type if there is no cross talk between them. So the other side also is like this, same. So essentially what I am trying to do is I am mapping this area, this p side and this n side. If there is no diffusion, nothing, no internal potential difference developed, it's just this much is p type, this much is n type, and what is the conduction band, what is the valence band, where are those energies for this entire thing. If you draw it, it should be like this. But it doesn't remain like this because of this. On p side, the potential has gone down. So potential has gone down. That means systematically you are changing the energy levels, all the energy levels upshift, right? Because what we are showing is the electron energies. These are the energy levels for electrons, and therefore potential and energy, you will have a negative sign in between, right? Energy is Q times V, like that. So if you have a energy level somewhere and then this extra energy is imposed, right? So that much shift will be there. So since the potential here has gone down, and therefore the energy will go up, each energy level will go up by Q times and this much of amount. So relative to the n side, let's do it relative to the n side and p side, the energy levels are shifted by different amounts. So relative to the n side, what happens? This P will go up by this much of energy. Q times energy, electron times E times VB. This much is the total shift in each of the energy levels which are there. So if I keep this here, each of these energy levels will be shifted up. Each of these energy levels will be shifted up. So my diagram should be rewritten, and I have to, this edge will now go somewhere here, and then you have all those energy levels. Okay. I'm just drawing relative to that n side. It's not that it stays here and only this shifts and so on. I'm only looking at the difference. Similarly, this edge of the valence band, that also shifts up by the same amount, and therefore it's like this. Why I have erased this much? Because this much of difference appears only away from the depletion region. Let's say this is the depletion region, after which the potential is constant here, after which the potential is constant here. So this difference that I have calculated is from here to here. That means well on the left of the depletion layer and well on the right of depletion layer. So that is this. And inside the depletion layer here, when you see a gradual decrease here. That shift gradually decreases. So if I take this as the reference, the shift is this much here, 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 and shift is this much here. All right. So gradually it will come and join here, like this. Like this. So that's the kind of energy diagram you will have. These are your valence energies, valence band energies, and these are the conduction band energies. So the band is shifted like this. This is P side and this is N side. This is the depletion region and so on. Now at this stage, I would also like to introduce a very important term qualitatively, and that is called Fermi energy. But that will be in the next lecture.